water inside the bowl is moving, the characteristic sound will change. And so our main focus is how to factor out water, perfect the sound with rotations, and how to predict the sound of water. This is my outline. And this is the observation. We can see that when we strike the ball will emit a regular sound when it rotates. Here, resonance and vibrational modes. The resonance occurs when you strike the ball, it vibrates at its natural frequency and creates a sound wave. And this presence of the water will alter this, frequency. And that further changes the vibration modes of the tank. Natural frequency. Natural frequency is a rate that the object vibrates when disturbed without any external force acting upon it. And when the natural frequency aligns with the frequency you struck the ball, it will create resonance. And they'll amplify the sound waves. And the natural frequency can be mathematically expressed as for the simple mass string system, that frequency equals to 1 plus 2 pi times square root of k times cross m. And k is the distance of the spring and m is the mass. Steady waves. Steady waves occurs when the sound wave travels through the opposite direction. And thus, steady waves will also further affect the characteristic sound of the ball emit. Damping effect. Damping effect. The damping effect is the initial condition to the dynamic system. And the amplitude of the vibration will gradually decrease until it comes to rest. And the mathematical expression can be expressed F equal to negative CV, which F equals to the damping force, and V represents the velocity of the oscillator, and C is a constant. And as the water rotates within the ball, it develops a free surface curvature and concentrated drag flow against the impacting volume that is altered by the rotation. And according to Flopdek's and conjugal force, the pressure flow can be expressed by this. And that means the pressure that the ball gives to the water gives to the ball. Flux motion. Since this system is expressed as a thin cylindrical tank, the flux motion is satisfied with this wave equation. That means the pressure affects sound waves. And this is my experimental design. I use a cylindrical tank like this and use a fishing line to make it hang in the air without any interference. And we put the microphone on the top of the string to make sure that the microphone is in the same place and in the middle of the ball. That can record at the same place. And we use the pendulum to hit the ball to make sure that every time the force and the position that hit the ball is the same. And for the experimental design, we first want to find the water volume, the relationships between the water volume and the fundamental frequency. And the method that we observe is that when we strike the ball and we record the sound and we put it into a study and we observe the spectrum and quantify it like this. And this is my result. This is a table of the last page, and we can see that when the volume inside the ball is 0, the frequency is like this, and so we can find the natural frequency. And respectively, the volume increase with 100 milliliter each time. And this is our data analysis. From our data, the left is the relationship between V, which is the volume of water, and the F fundamental frequency. And we use a log-scale line to fit the chart, and we can see that the frequency is proportional to the square root of the water volume. So we can echo to our theory of simple mass spring system, that the natural frequency is given by this. and K equals to the stiffness of the spring. And compared to that, our mass can be varied as the volume of the slot inside it. And for our second experiment, we want to find the relation between the water condition and the spectrum differences. And that we record, as we experiment numerous volumes of the water, we can see that when we rotate the ball, we can have a spectrum like this. And the spectrum have those frequencies that can echo to the volume of water when it is still. So we can further have the conclusion that the frequency when the water is rotating is the addition of the water is still. And also, we want to find the relation of the damping effect in this experiment. And we find out that the damping effect will only affect the energy loss. So that doesn't affect the frequency of the water. And also, added on to this page, the M flood that means the volume of the water inside it, because volume further affect the mass of the water. So that also echoes to the pressure field of my theory that when the mass increases, the pressure will also increase. So for the conclusion, we can predict the frequency of the ball element. We can imagine the tank is form of countless springs. So that if the tank is formed as countless springs, we can further predict that how many pressure we added onto the spring is like how many mass we added onto the spring. So that will affect the frequency that it emits out. And the damping effect only reduces the energy and will not change the frequency. And the frequency is approximately inversely proportional to the square root of the water volume. And the frequency rotating is addition to the frequency at rest. And for the further experiment, we want to further focus on the frequency that change at different parts of the tank and find out how different frequency interfere. And we want to experiment on how more material will investigate and vary up their temper. And that will be my presentation. Thank you.
Okay, this is a moment from the interviewer. I have a few quick questions to ask you. So first, can you please turn to page 7? So here you mentioned the damping effect, and you mentioned the damping force and also the velocity. I would like to ask what is the damping force?
The damping force is a force that will decrease the energy. Like if you rotate, the water will give the energy, right? But the damping effect is that will decrease the energy that the water is rotating. So that will come to rest as it ultimately comes to rest.
Then where is the damping force from? Is it from an external force or from the rotation?
It's from it's the friction between the water and the tank.
Okay.
So it depends on the material of the tank.
So then I think that the velocity is talking about the velocity of water, right?
Yeah.
Okay. And can you please turn to page 8, next page. So you mentioned according to fluid statics, so you get the equation.
Yes.
Then I would ask if the water is moving, is it still suitable to use fluid statics?
Yeah, because it mentioned about the speed of the water rotating.
Okay. And can you please turn to page 10? So here you mentioned that you attach a microphone on the fishing line.
Yeah.
So when you move the water towards the microphone also moves.
Yeah, but we put the microphone on the top of the fishing line. So you can see that on the top of the fishing line, it will not move.
So you didn't move the water?
What?
Did you move the water in this design?
Yeah. We rotate the water, but the microphone is on top of it. So
Also, then you rotate the water.
yeah, we rotate the water.
Okay.
And this,
And
we rotate the water in experiment 2, but not experiment 1.
okay. And can you please turn to page
Time's up.
sorry. And this is a problem statement. When you strike the side of a metal ball containing some water, you can hear a characteristic sound. The sound changes when the water in the ball is moving. Explain and investigate this phenomenon. And the main focus on this problem is how the factor that will affect the sound wave. And this is a summary of the reporter. So for this theory, they use resonance and vibration mode, and also the natural frequency, and standing wave, damping effect, the pressure flowing in water, the fluid's motion, and also centrifugal force. And this setup is cylindrical tank, fishing line, pendulum, and microphone. And the parameters they discussed is the water volume and the conditions of water, which is upright or rotating. And they think that the frequency is approximately inversely proportional to the square root of the water volume. And the damping effect will cause energy loss. And this is the overall advantages and our suggestions for the reporter. So first, what they did very good is they have a detailed discussion about comparing the frequency of the water rotating or not. And yes, they have a comparison of rotating or not. And they also have a clear explanation on each part of the theory. However, we think that they do not have enough qualitative explanation on what causes this phenomenon. And also the lack of considering the error in their experiment data. And I think that they need more quantitative explanation in their data and also their theory. And these will be the points of discussion. So I would like to invite the reporter to discuss with you. Okay, so first, according to the problem statement, it says that you will hear a characteristic sound when the water is moving. Then can you explain to me what is a characteristic sound?
So the characteristic sound is that when the ball is rotating, you'll hear the sound. And the sound might be different from volume, frequency, like the high and low pitch, when it's rotating.
So you think that the characteristic sound means the change in frequency and the volume?
Yeah.
Then did you try to analyze the volume in your experiment?
Oh yeah. Volume actually volume is mainly affected by the damping effect because volume is equal to like energy, right? Like energy is higher, volume will be higher. So we consider the volume as like the energy most affect the volume.
Okay, so I think that the volume will be decreasing over time, is that correct?
Because
And this is because of damping cause energy loss. Okay. Then what about the frequency of the characteristic sound? Will it increase or decrease?
The frequency actually will decrease based on the volume of the water.
Okay. So can you please turn to page 6. So you talk about the standing wave in your theory. Then I think that if you talk about the standing wave, this means that they will have different frequencies at the same time.
Yeah, with the opposite.
Then can you share it in your experiment data about any effects on standing wave?
Oh, actually, in my experiment, I only consider the frequency because I think that the frequency is mainly about the characteristic sound. It's a main factor.
I mean, if there is standing wave, there shouldn't only be one kind of dominant frequency, right?
Yes.
Like there is, you can hear a lot of different frequencies if there is standing wave. Yeah, so in your experiment data, can you show me like which peaks are the standing wave?
Oh, we think that when the peak is high, there might be standing wave happening because they will have a louder sound. That means they might travel in the opposite. They might add it on each other, so that will create that peak.
Then do you think that the peak of different frequencies for standing wave will always be the same type, the peak? For the different frequencies, like in different frequencies, will the peak always be the same for the standing wave?
I think that's mostly about the energy you give it.
Yeah. Okay. So I think that according to standing wave theory, I think that the natural frequency of the standing wave should have the highest peak because it is the most dominant
I think
frequency.
that's what it means resonance.
Well, I mean like the base frequency of the standing wave. That should be the
You mean the
dominant.
fundamental frequency?
Sorry.
Fundamental frequency.
Yeah. So I think that you can show like you said, the fundamental frequency in your experience data to show that it supports your theory of standing wave. Do you agree with me?
Yeah, so we find the fundamental frequency of every volume of the water.
Yeah. How do you find the fundamental frequency?
So we analyze the spectrum and we find the times like the peak of every frequency, and if that because fundamental frequency is like three times.
Maybe sometimes more than 3, but yeah. So.
Yeah, that is different. So we find out the relation between each peak.
So if it is like 1 times the peak, or 2 times the peak, or 3 times the peak, then you think it's the frequency of standing waves.
Yeah.
Okay. Then can you please turn to page 7? So I want to talk about the damping effect. You said that damping is mainly on the volume of the sound.
I don't think damping is the main effect of this.
No, I mean it affects the volume of the sound. Is that right?
Yeah.
Yeah. So can you explain more on how what is actually the damping force? I'm still not very clear about it.
So can I use the whiteboard? So like the damping effect is when you use the paint and the water rotated, right? It will contact with the wall of the tank.
Yes.
And this is the flood motion,
Yes.
and the flood will have friction in there. And it will make the energy loss.
How will it have energy loss? Is it because of the vibration of the wall?
Because of friction.
So you think
Friction
that
to make the flood and the tank.
yeah, so you think that after you hit the wall, the vibration will have energy loss? Because you want to hear the sound after it hits the wall, right?
Yeah.
So after it hits the wall will have vibration.
Yeah.
Then will this vibration cause energy loss?
No, I think it's only about the tank and the flood. And so when it's vibrating, they might absorb that energy because it might absorb additional energy.
Yeah, okay, so I think that maybe you can state this more clearly in your damping effect, because I think that both the vibration of the wall and also the friction of the water in between the friction of the water will both cause the damping effect. And I think that another better way of stating your theory is to try to find the damping coefficient to actually calculate the energy loss.
Actually, I didn't focus on that point because I think the most important factor of affecting the characteristic sound is the frequency of the sound. It's not the volume of the sound.
Okay, I get it. Then can you please turn to page 15? Yeah, so why are you connecting the lines in the graph on the left? Like the left-hand side. Is that like a line of your theoretical data or theoretical?
That's the fundamental frequency and the volume.
So is this a theoretical line or is it?
No, that's the line of our experiment.
So why can you like connect the lines between each data? Are you meaning that the relation of frequency to volume is linear in between those data?
Because we want to see we want to see the trend between when we add on the volume of the water, how will the frequency change? And we can see that the trend is.
Yes, so I want to show the trend.
Yeah.
Yes, I think that a better way to express this is by using maybe the best fit of line or maybe according
So
to
we
your
use log scale to fit it.
Sorry?
We use log scale to fit it. and we find that relation.
Oh yeah, okay, but I still think that it is not appropriate to connect lines. I think that.
So we have the ultimate relation there.
Okay, and how about the error in this experiment data? Do you have any error calculation, and you didn't add any error bars to your data?
Oh yeah, I think that's my loss.
Yeah, then how do you know that it's zero? Sorry, how do you know if there's any deviation between the zero and experiment? If you don't have error bars or you didn't calculate the error.
Okay, so I think that's my loss, but at the end, ultimately our results that are zero.
Okay, so you agree that you should analyze more on the error of the data and try to calculate it.
Yeah.
Okay. Then can you show me experiment 2? So here you are trying to change the water temperature. Is that correct?
Yep.
So when you rotate the ball, are you using your hand to rotate it?
No, this is just the observation video, but we rotated him with the experimental setup like this.
Can you show me? Can you tell me how you rotate the ball?
So we rotated, we rotated with our hand, and we recorded, and we analyzed it if they are rotating the same height and speed. We recorded to analyze the speed. We recorded for a long time, and when the speed is the same, we will cut that part of the video and analyze the result.
Okay, I get it. So I think that the better way to do this experiment is to try not to rotate it with your hand and try to use the machine to rotate it. So that
We
we can
standardize the rotating speed and the rotating height, so they will all be standardized in the
yeah, but
video.
it will still cause a larger errors than the machine. Yeah, so I think that is a better way to do it. And also, did you control the rotation speed? Like, did you try to do different rotational speeds in your second experiment?
We standardize the rotating speed. We standardize the rotating speed, so we make sure that all the rotating speed is all the same in every experiment.
Okay, can you turn to the page with your data for experiment 2? Yeah, so what is the rotating speed of this experiment? Like, at
We
what
didn't
time?
measure the rotating speed, but we standardized the rotating speed. But we didn't measure the rotating speed. What we want to show in this result is that the rotating frequency is addition when the water is filled.
Okay, so you only want to compare rotating and not rotating.
Yeah, because we are curious about
So
what
you
is
think
the
that
frequency
so
of
you
the
think that
frequency.
for different rotating speed, it will always happen the same thing.
Yeah.
Okay, so I think that this is not very adequate to just do only one standard rotating speed and then compare it to not rotating and say,
Well, actually,
Yeah,
in our
accuracy.
observation, when we rotated quicker, the water will.
yeah, so I think that maybe you should quantify the how much the rotating speed is and try to do different rotating
Yes,
speed.
this is our further experiments, and we think that is a good point to discuss about.
Okay, thank you for this question.
You can summarize your discussion.
Okay, this is a summary for the discussion of the whirling ball. And first, we talk about the effects of the standing wave, since they talk about it in their theory. And we think that they should show more clearly which frequencies are the frequencies for standing wave in their experiment. And also the explanation of the damping force. And we think that the damping will also be caused by the friction and the vibration of the wall. And they should find a damping coefficient in the theory to show that they are right. And also they can calculate how much energy loss is in the vibration of the wall. And I think that in their data, they should connect two dots if there is not enough experiment data between them, even if they are only trying to show the trend. And they should have done some error calculation in the experiment, and they agree with me that the error is very important for the experiment. And I think I should try not to rotate by hand and try to do different rotational speeds. Thank you.
I question want to ask both opponent and reporter. Because because in reporters observation, you use your hand to hold it. But do you think the hand will affect the sound?
Yeah, I think the hand will absorb the energy of the rotating.
I also think that the hand will absorb some energy.
Okay, and the next one is, do you think that whole system will have energy loss?
Yeah, I think the friction between the tank and the water will firstly absorb the energy, and secondly, the contact with the fission line, even though it's small, but it will also absorb some of the energy. And also the air will also affect the energy.
Are you talking about the system of the bottom of the ball? Yeah, I think it will have energy loss because of vibration.
Okay, and the next question, and for both, because the reporter used the microphone to record the sound, do you think the environmental sound will affect the data, and the data will be accurate or not?
Yeah, we actually make sure that we are in the silent place, but it will still have some environmental noises. So we will, yeah.
Yeah, I think that the background noise should be considered just an error of their experiment, and they should try to remove it.
Because the reporter didn't mention that when the ball that is moving and where you hit.
So like we use the handle to make sure that every time we hit the same spot.
So do you think that the different position you hit will affect the sound?
Yeah, because when you hit the spot that is underwater, like if there's water inside it, it will actually have a lower frequency because it will absorb some of the energy. But when you hit the point that don't have water inside it will have a louder sound.
Okay,
Yes, I think that different hit points will generate different frequencies.
and the last question is, because the force you rotated is different, so how can you make sure that your result is matched the theory? Can you tell me for that? Like what force? Like you use you
Pendulum?
Yeah.
Oh, because we put to the same height, so the force is the same.
Okay. Okay, that's all my questions.
By the preparation time.
Okay, I'm ready.
Okay.
So I'm a reporter from Team Yujin and I'm Yang Chenzhen. And today the problem is the welling ball. And here is a problem statement. When you strike the side of a metal ball containing some water, you can hear a vibrating sound. And actually we are mainly focused on, and we have to explain and investigate this phenomenon. And our main focus is how the factor of the water will affect the sound wave. And here is the summary of the reporter. So there actually has a lot of theory that natural frequency, standing wave, damping effect, and also like pressure field in water. And here is the experiment setup. They use a fission line, cylindrical cage, microphone, and pendulum. And here is the parameters. It's changing the frequency, water volume they add, and also the water condition. And here is like proving the strength of the reporter. They use a lot of theory to explain this phenomenon. And they also use a lot of formula to explain. And there's spring that specialists they have listed their future plan. And here is some suggestions for the reporters. There are actually lots of videos and audios. I think audios and or video is really important in this topic because this topic is mainly about sound. And they added up data to support the theory. Didn't explain the results so much. Error bars didn't consider the errors. And here is the opponent part. They actually focus on the water frequency changes and what will affect the water volume. And also, they ask the reporter to explain theory that is good and estimate details. But the suggestion is don't cost too much time to focus on the single question. And here is the question. The reviewer I asked, if the head evade a sound, reporter answered yes. Do you think the environmental sound will affect? And do you think that the position they hit will affect? And the reporter all answered yes. And that's and I think that there's some mispoint in the discussion is I would say that. And they actually didn't focus on about the data part. Like I remember that a page where x-axis didn't mention what the x-axis is. And I think it's a part I didn't do very well. And also, the opponent didn't tell the reporter to explain how the formula comes and didn't explain what the formula is. So that's actually all of my report. Thank you very much.
Reporter.
We think that resonance occur when the frequency, natural frequency, meet the point that we struck the ball. And we think that the frequency is more important than the volume in this experiment, since the frequency is highly considered and very obvious in our observation, which means that damping effect is not really the main theory in this experiment. Which we believe that the simulation of this. We believe that this is a good theory for us to simulate the tank as numerous springs, which I'm really disappointed that the opposition didn't totally fail to focus on this simulation. Which I'm really disappointed that opponent failed to focus on this simulation. And we mainly aim to find the relation between the spinning and not spinning. Since we find that we observe that when the water is still, it will not have that characteristic sound. However, when it's spinning, it will have an obvious characteristic sound. So we think that most importantly is to find the relation between spinning and not spinning. However, the opposition keep focusing on the however, the opponent keep focusing on the little point that we don't think that is very important. So this is our final model for this observation. Thank you.
Now is the time for the vote. Okay, Professor Hai. You want to go first?
No. It's fine. Okay.
Based on your result, you mentioned you use the tank as an inverse spring. So, what makes you think that?
Because we find that the relation of the volume and the volume of the water and the frequency has the proportional relation, right? And the proportional relation echo the natural frequency of the spring. So we're like, maybe we can simulate it as numerous spring, which means that there's very many little springs that consist this tank.
Okay. I noticed there is a formula that you mentioned at the max.
Yeah.
Yes. But, are the other bottom, or the other bowl. The other bottom of the bowl.
So that means that when the tank is have a the water is higher, that will have it's like a spring.
I mean the shape of materials. Because I think it's just a coincidence. It's not perfectly.
Actually, we consider that. There's a numerous spring here, and so when the water is higher, then we can consider that those springs are having a big mass on it, and those springs don't have a big mass on it, and that will further affect the air inside it.
Next question.
That's Professor Sai.
Okay. You take a cylindrical container, right?
Yeah.
How can you simulate it with continuous spring? Because the cylinder, when you strike it, the vibration is wall is vibrating. And for a spring, it's up down, up down with the oscillation. How can you?
We think that it can.
No.
It will have a similar relation. So we have a similar
No.
display.
But I want to ask others, can that be done? Can this model be supported that they think that the cylindrical bucket is like a continuous spring? First, your opponent, I think we should have something.
They didn't prove that in their experiment data, so I
But
think
do you think it's valid? Is this,
no, I don't think so.
how about you?
I don't think so.
Why? It's obvious that you use the standing weight, but that's the standing weight for air columns. I fail to see these connections. That's just the air column, open and close, and you just show that. That has nothing to do with the sound emitted by the bucket, isn't that?
Sorry.
That is, you shouldn't mention. I think what's the point of showing us the standing waves of air column? You think the sound is emitted by air column?
Standing wave might affect the characteristics now.
Standing wave for what? That's
Okay.
air column.
But the standing wave that
No, I'm saying the sound emitted by your container
yeah.
is not the same as
Because
this is the air column. At most, you can say the air column above the water, and then I believe.
Yeah, because the sound
But
is
that's
when the wave is inside the container. The air inside the container is waving. That will emit a sound.
I'm very interested in the opinion of the other two. Do you think the sound emitted is by this air column?
No, I think that the sound is emitted
Okay,
by the
I'll review. I will use what's your answer? What's your answer?
Can you repeat the question again?
Do you think the sound emitted or the sound they can analyze is due to sound emitted by the air column? That's air columns. Saying is that clear, open, and close end, standard diagrams on textbook, right? But that's air column. Air column, you have a tube, you have water, then you have air column.
Yes.
And if this is open at one end, right? And they think that that's the sound emitted by. Taking too much time. My thing that should be shared.
So, further questions?
Excuse me, will you do something? You want me?
No,
I have so
sorry.
many questions, but I think I
As a speaker,
agree. I'm pretty sure what I should do.
so it's ready. Let's finish the story. Ready?
Yeah.
Okay, so let's show the score for the result. 6, 4, 5, 6, 6. The score for the opponent 7, 6, 6, 7, 7. And the score for the reviewer 6, 5, 6, 5, 5. Okay. So